So, afternoon, everyone. Meanwhile, the participants are joining.
Good
We can
afternoon.
start the session, and this is the second session of first day of FDP. So, we are having with us in this. I think this is the fourth lecture of today's session. So, in this lecture, uh, we are having with us an eminent personality from NIT Jamshedpur, uh, Professor Prabha ma'am, and she is a professor and dean faculty welfare in the Department of Mechanical Engineering at NIT Jamshedpur. So, with a distinguished career spanning over 25 plus years in teaching and research, she has established herself as a leading expert in the field of solar thermal energy and thermal engineering. Her primary research interest includes the solar energy, thermal energy storage.
Hello, good afternoon, ma'am.
Good afternoon. So can I start?
Yes, ma'am, you may start.
Okay. So good afternoon to everyone present here in this FDP. And first of all, I would like to thanks to the organizing team of this FDP for inviting me to this session. And as I am the faculty of mechanical engineering and the research area is thermal. So I will give some thought about my area, and it is not a lecture session. It will be a just interactive session with the other persons also. So my request will be to just
Yes.
interact with other persons who are present in the online mode.
Yes, there is some problem with the server, I think.
Okay.
Okay. So I was explaining ma'am's
Okay, no problem.
background. So currently she is the principal investigator for the significant research projects,
Okay.
and she has been funded with various uh, funding agencies for several projects. He
Yeah.
has also serving as head of mechanical engineering department, chairperson of the Institute Computer Center, dean of faculty welfare, and her current role as professor in charge of outreach activities. And she has also been awarded with the Lady Engineering Award from the Institute of Engineers in 2019 and the Distinguished Women in Engineering Award 2018. So we are very fortunate to have you, ma'am, here in this session, and we would happy to hear from you on the topic solar thermal energy. Thank you.
Okay. Thank you. So let us continue. And now I would like to share some points on the solar thermal energy, which is connected with the advanced thermal technology for sustainable future. So first, I would like to say that why this solar thermal energy we are focusing on in this new era of generation, because as we know that the energy which is the main source of economic growth of any country, and for India, with respect to the global growth, we are pacing to achieve our target by the PM Modi's planning Viksit Bharat @ 2047. So with that goal, we are now trying to achieve the economic growth of India with the help of energy sector which are available and growing day by day, so that we can achieve our goal in the early time before the targeted time. So we can know that we see that this industrial revolution was came into the picture in 1870s, like that, when the steam engine, or in the 1780s when steam engine was evolved and invented. And after that, when the IC engine, internal combustion engine, started to work, that brings the industrial revolution to all over the world. And after Second World War, the energy demand increases in a vast way. So people were using everywhere the fossil fuels in every sector, either in industry or in home side or automobile sector. Every industry begins to use this internal combustion engine for their purpose or for their uses, and we began to start depleting all the minings and like coal sector or oil sector or like that. So now the time has arrived. That means we are fearing of depletion of or shortage of all these fossil fuels, and the time has come to think about the alternative source of energy which are available, or which we can say that available as an alternative source of energy for the industrial purpose or for the power sector. So now we can say that this industry on the global space requires 30 to 32% of the energy. Out of that, 25% we are emitting direct CO2 to the environment. And this is a very, very dangerous to our planet. So we can say that we have to think about the other sources of energy. And besides all the different kinds of alternate source of energy, that is tidal source of energy or wind energy, we are opting for the solar energy. Why? Because this is available abundantly all over the world. It is boundaryless. We can't control to a particular site this solar energy. And the temperature variations for the different industries are available for the use of this solar energy, because there are different category of thermal heat uses, and solar energy can fulfill the gap of this demand and the supply of this energy. So that means 60% of the industrial heat demand, which are less than 400 degrees centigrade, can be directly fulfilled by the energy developed from the solar thermal. So here in the pie chart, you can see that the most of the part of this is like solar thermal power or the energy which are less than 400 degrees centigrade. And LOCH of the solar thermal process heat fell below the 3 to 5 rupees per kilowatt hour in the Sunbelt regions. That is the data source. So we can utilize this solar energy as our sustainable energy for the future demand of the energy. So according to the market size and growth, recently we have seen that for the installed solar power plant in terms of global, that is 28 gigawatt of thermal. And we are expecting this growth in the CAGR of percentage, that is 22% will be in the 25 to 30. For the India, at present, the solar thermal power plant, which is available in the terms of 0.18 gigawatt of this thermal, we are expecting it to achieve at the rate of 45% to 50 gigawatt thermal by 2030, as per the MNRE resources. And for the Middle East and the North America, Africa, which is at 12 gigawatt, it will achieve 18% by 2030. And for the most China, which is at the 5 gigawatt, that will also grow at the rate of 15%. So we can see that every country as a whole in the world are more focusing on the investment on the solar power. So in this way, we can say that India is also focusing in different way to invest in the solar energy. So you can say that this high DNI, we can say that the investment or the present direct normal irradiation available in the Rajasthan as the 2400 kilowatt hour per meter square per year, we are seeing this. Also in the Gujarat, it is 2300, and in the MP it is 2200, and Ladakh it is 2600 kilowatt hour per meter square per year we are achieving. And to focus on this achievement, like continuous growth of the energy demand in India, government has given different schemes, or has given the investment or funding in different kinds of a scheme to promote the research and the technology transfer or the development of solar power. Like in the MNRE funding is 5,000 crore is available or giving to the different organizations. Like this, also PLI CSF is 2,400 crore rupees. The government is giving for the erection of the solar power to like different kinds of yojana, government yojana, and CFA is also of 50 crore. So these are the different kinds of projects on which government is investing money to promote the work in the area of solar energy. So by this, India is focusing to promote and to achieve the target day by day in a vast way. So the main key players in India in the current situation, we can say that different companies have come forward to promote or to help India to achieve our target. So first of all, Adani has come forward as a developer and investing in 50 megawatt thermal power at the Kutch. Thermax also as the engineering, procurement, and construction on the solar power plant as the in Gujarat, like 30 megawatt of thermal power. And as well also has come forward as a receiver of the solar power in the Bikaner as a concentrating solar power plant. So Plastech is another company which has come forward for the fission material storage at the different 10 plus pilots as the investor. So Glasspoint is another company which has taken and closed rough with the collaboration with ONGC AOR project. So these are the different companies which have come forward in the mission of our PM Modi's achievement, that was Viksit Bharat. So these are the fundamentals. Now coming to the solar thermal power plant or works, which are comprises of the different levels of the solar energy. That means, so first of all, the concentration, and which focuses on the mirror work. That means sunlight, we are focusing by the mirror, sunlight focusing to the collector. So this is one part of the concentration or achieving the solar power, solar energy. And the second part is the absorption, how we are absorbing the solar energy. That means the receiver that converts the direct solar energy into the different medium as a heat source. And the third one is the transfer, heat transfer fluid that collects the heat, solar energy in the form of heat that carries forward for the utilization purpose. And then this storage, that means thermal energy storage, which absorbs the solar energy as the heat energy for the 24/7 supply to the as per requirement. So at the different levels of uses, we are using solar energy in terms of the steam, hot air, or power, or the fuels. So this picture shows from which time we are using solar energy. That was, this picture is the oldest pictures where Austin Mosset's largest sun was seen or display at the Universal Exposition in Paris 1878. That was, so we cannot say that solar energy we are using nowadays. It takes times of 100 years to develop this solar energy as an alternative source of energy, because this was the first time when the people were thinking about how we can capture the solar energy for our domestic purposes. Another picture, which is this another sun motor 4 HP solar thermal power steam engine in farm in Arizona, 1904. So we can say that these pictures depicts that one concept, that is Rome is not built in a day, means we are trying very hard from 100 years ago, and now we are thinking to apply it in a vast way. So from the beginning to the end, many development has been done in the capturing of solar energy. So there's also an old picture of Bell System solar battery converts sun rays into electricity, was the advertisement from the Look magazine of 1956. So that concept, when solar photovoltaic cells come into the picture, and the thermodynamics of converting the solar energy into the electrical energy. So now we can say that this utilization of solar energy is of having the various uses, and we can use this solar energy So here we can see that in this picture, solar energy can be utilized in two ways. First is the solar thermal, and second one is the solar photovoltaics. Solar thermal energy we can use for the purpose of heating and cooling. In terms of heating, this energy can be used as a solar air heater where air is heated, in the solar water heater where water is heated for the utility purposes. And the third one is the drying of agriculture products, where this heating solar energy in terms of heating process can be utilized for this drying of agriculture products. Another purpose is cooling by the solar energy can be used for the vapor compressed refrigeration cycle to storage purpose of the foods in the cold storage as a cold storage. Another utilization of the solar energy is as a photovoltaic cell in the solar pumping or the electric power generation, we can say that. So thermal collectors and its application, first we can see that this solar thermal collectors harness sunlight to generate heat and then making them ideal for heating, cooling, and industrial process. As of current situation, global capacity stands at 392 gigawatt of thermal, with India at the rate of 3 gigawatt of thermal installed, driven by subsidiaries and the National Solar Mission. Under this mission, we have generated this solar energy and utilizing it. How solar thermal collectors works? First is the principle of this is to absorb solar radiation via dark absorber plate coated with high absorptivity and low emissivity. That coating increase the absorption power of the plate, and then heat transfer, that means sunlight, warmth, fluid, water, glycol, or air as per the utilization, which is circulating through the pipes or tubes, which collects the heat from the collector, and then it is utilized as the output as per the requirement of the industry at different temperatures. So this is the types of solar thermal collectors. Flat plate solar collector, that means it absorbs on the just of different design, having collector design placed in the insulated box with the glass cover. But the temperature range of this is very low, that means 30 to 80 degrees centigrade, up to which this flat plate collector we are using. And the efficiency is also very less, that means 50 to 60%. But the advantage of this is that means it is very simple and cheap. And but the disadvantages, its losses, heat loss is maximum in this case. Second types of solar thermal collector is vacuum tubes, which is made of glass tubes with vacuum insulations and selective coating upon this, and the operating temperature is 50 to 150 degrees centigrade. It is slightly, its efficiency is slightly higher, and it can be utilized, but the costly is, it's some costly than flat plate. Another is parabolic trough, that is the curved mirror focus light on tubes at the focus point, but the temperature we are getting higher, in this case 150 degree to 400 degrees centigrade. So it is of a very use in the different domestic purposes, like in hospital or in big areas of food cooking like that. There we are using parabolic trough, and as per the requirement it is utilized. Next is your dish or heliostat collector, that means a point focus mirror to the center receiver. Here we are getting very high temperature, like 300 to 1000 degrees centigrade, and its efficiency is obviously is very high. So it is utilized in the industry where high temperature water or the liquid we are required, but at the same time its cost is high. So we can say that solar water heater is just concentrating solar energy and over a time gradient, and its uses from the heating to the pool water or hot water for the simmering or domestic use. But the most utilized of this, we can say that in the at different temperatures of hot water. And the simple design of this is given in this here. That means conductive thermal collectors painted with black to absorb maximum solar energy. And then a transparent cover is to capture solar radiations are placed over this, and pipes for water flow, some insulation, and water body as per the structure is it is very simple to use. And passive design, that means we are not providing a motor to circulate the cold water and hot water, but due to the density difference, it is circulating according to the design. So this passive design uses thermal convection to circulate heat in the water system. So and this is simple example of this passive solar water heater design. So it is a natural circulation is given. And for the active design, we have to provide the pump to circulate the water from the cold storage to the hot water system. Application, we can say that in a household, heating and cooling costs are among the most energy intensive domestic activities. And solar water heater can replace the cost of heating water for either a pool or the hygiene uses. To demonstrate the ability of a solar water heater to offset domestic uses, interns will set up a solar water shower and the hot tubs. Other is heating can be provided to a bioenergy activities to increase efficiency of process or make the process more energy independent. So we can say that solar collector should be placed facing south and at an equal angle to that of the latitude of that place. That is the most efficient way to place the collector position. And to increase, again to increase efficiency, angle should be increased by 15 degrees during the winter season and decreased by 15 degrees in the summer. This is another method. So this makes the angle to the sun closest to the 90 degrees during seasonal changes. And now coming to the solar air heater, which is another application of the solar energy in terms of domestic and the commercial purpose. Solar air heating system. The solar technology in which the energy from the sun insolation, that means incoming solar radiation, we are capturing it by an absorbing plate and using air as the medium. Solar air heating is a renewable energy heating technology used to heat or conditions air for buildings or the process heat applications. This is a simple design of a solar air heating for the passive design. That means a box is made of or insulated in between a solar absorber plate is placed. A glass cover is placed on the top of the box to reduce the wind losses, heat losses, and the fluid like air is passing through the bottom box of the bottom side of the absorber plate. And this absorber plate is blackened, made of GI or copper or aluminum sheet. So these are the specification of simple solar air heater. This is the practical picture of the passive solar air heater design, where no motor is fitted in the system for the circulation of the air due to the hot air and cold air density difference. The movement of this takes place. This is another example of the solar air heater with herringbone fins. That means fins are provided under the absorber plate to increase the efficiency of the solar air heater by providing more surface area. And as we know that the heat transfer is dependent upon the surface area of the heat transfer. So due to that, we are increasing the efficiency of the solar air heater These are some basic equations for the energy balance equation for the absorber plate, bottom plate, and the air for the fluid convection heat transfer. We are using these equations, and in the pictorial view, we can show that how the energy balance for the considered control volume for the absorber plate, bottom plate, and the air flows takes place. And upon the calculation or the taking the data of the temperature, we can calculate the thermal efficiency of a solar collector, which is the ratio of the useful heat energy gain to the total incident radiation on the collector during any time of period, any period of time. And thermohydraulic efficiency, after calculating this Q, we can calculate the thermohydraulic efficiency also, and upon which we can say that this solar air heater is how much efficient. So we can say that there are different types of solar air heater depending upon the different collector design. That means a double exposure collector, honeycomb collector, thermal trap collector, two-pass collector, overlapped glass plate collector, artificial roughened absorber solar air heater, packed bed solar air heater, extended surface absorber solar air heater. So these are the different types of solar air heater based upon the collector design and the heat capacity resistance of the material. So these are some picture of this different types of solar air heater. That means double exposure flat plate collector. Top and bottom both sides are placed solar absorber, and between them air is flowing. Another is honeycomb collector. So these are the design of the different types of collector. Overlapped glass cover solar air heater, roughened solar air heater of various size or shape. These are the packed bed solar air heater and the extended surface absorber solar air heater. That means we have provided fins at the bottom of the absorber plate through which air is flowing. That means we are providing more and more surface area for the heat absorber and then for the heat release to the air. So application of solar collectors, you can say that this is solar cookers, solar chimney, parabolic trough, solar distillation, parabolic test, solar water heater, solar air heater, and central receiver system are the main utilization upon the according to the requirement. Solar cooker as just a concept of the solar heater, solar energy to cook the food when we are concentrating all the energy, solar energy to a certain focus point. That means solar cookers or ovens are primarily used in developing nations as a primary method for cooking using passive solar heat to cook the primary meals. Insulated box that collects solar radiation enhanced by reflectors attached to each side, and that helps combat the deforestation. So these are some examples or picture that means solar oven in the Nepal we are using. And parabolic trough is another types of solar collector. That means parabolic trough concentrates sunlight along a special gradient into a linear focal point, and the fluid acts as a thermal sink as it passes through the tubes along the focal point. So parabolic troughs are used to generate electricity but are subject to seasonal changes. So that's why this is another industrial parabolic trough. Here pipe is provided at the focal line of this trough collector. So this parabolic disk or solar furnace is a large reflector that concentrates thermal energy into a single focal point. And this focal point can contain a Stirling engine to generate electricity, or the energy can be focused and used in industrial process. So on a small scale, a reactor can be used in the same way as a solar oven. Another central receiver system that uses a series of sun tracking mirrors called heliostats to concentrate sunlight into a focal point. So this focal point contains salt that when molten generates electricity in a steam generator for large scale energy production. And these are capable of producing electricity over a 24-hour cycle due to salt's ability to retain heat. So these are some picture of central receiver system. So another one is solar distiller, and this solar radiation heats up the contaminated water and allows the water to evaporate, leaving the contaminated behind. So this system design collects distilled water for use, and the technology purifies water and can serve from one person to a community depending on the size of the system installed. So this is the basic picture of solar distiller technology. Another example of the solar energy is solar chimney. That means ambient air collected within the chimney rises as it is heated through solar radiation and drives a turbine, and that generates electricity. Base captures heat through absorption of a black surface and trapped by a greenhouse interface. Very inexpensive solar collector technology. This is just one example set by the Spain to erect this solar chimney power plant. Another uses of the solar energy is photovoltaics. So this photovoltaics is nowadays a common topic for using or capturing solar energy, which captures the solar energy and generates electricity by absorbing sunlight, and that light energy to create an electric current. There are many photovoltaic cells within a single solar panel, and the current created by all the cells together adds up to enough electricity to help power your home. So these are some types of solar cells we are using: polycrystal ribbon type and thin film, single crystalline silicon, polycrystalline silicon, and the thin films we are using as a solar cells. So nowadays, emerging technologies are arising in the area of this nano solar techniques. That means nano solar electricity conductive plastics, Konarka polymer, and dye sensitized solar cells have flexible cells about 5% efficient. So many research are going on developing this different types of solar cells, which is the recent past area of the research area. So this is energy tight bit is a solar cells in the early 1950s were about 0.5% efficient, and today a model is about 15% efficient. So this shows how we have developed this solar cell technology to generate the electricity, and we can say that this is the future future generation of electricity equipment. In comparison to 1950, you can say that how much area has been reduced from 2400 square feet to 60 square feet for the generation of 1 kilowatt of power. So this is the different types of typical PV system, standalone and the grid connected power. This is some examples of installation of the solar power on the roof of the commercial building. And this is the latest technology that means we are using in the solar power e-cars. So nowadays solar power applications in terms of photovoltaic cell has been developed in different areas of utilization. That means not only e-cars but also in any area, not a single area has been left which is using a solar power generated battery system. Or e-vehicles have come around from the solar vehicles to the solar powered e-car to the EV vehicles has been now come as another alternative source. So we can say that for sustainability of our future or for the energy, we have to convert our mindset, our thought from the fossil fuels to the new generation of this energy source, which are more sustainable in comparison to the our conventional source of energy. So with this, I end my session here. If you have anything to ask, please you go ahead. Thank you.
Thank you.
Hello.
Yes, ma'am.
Yeah.
So, participants, we may have a questionnaire over here. Anyone wants to ask some question, they may float in chat box over here. I think they have no questions over here, ma'am.
Okay. Thank you.
Thank you, ma'am, for giving your valuable time, and it's our pleasure to be you with in this FDP. So once again, thank you, ma'am.
Okay. See you. Thank you. Thank you so much. So
Aman?
can I leave here?
Yeah, ma'am, you may leave.
Okay. Okay. Thank you.
Aman? Himanshu?
Yes, sir.
Next candidate participant resource person कौन है?
Sir, me. I am the next part.
Okay.
Next
For
speaker.
a lab session, right?
Lab session.
Okay. Please go ahead.
Okay.
So before that, let me introduce you. So we are so good afternoon, all of you. For our next session, let me introduce to my research scholar, Himanshu Pachori. He is currently working in the direction of solar air heater, which is integrated with energy storage system, and we are in his research work. He have developed a double pass solar air heater, which is incorporated with phase change material, and he have about published 3 research article in SCI Q1, and likely going to submit his PhD thesis by end of this December. And in this session, he will going to enlighten you about the lab session associated with his PhD work. So, Himanshu, you may now take up over here.
Okay. Thank you, sir. I will take it.
Or we can wait for 5 minutes
Yes.
break.
Yes, doctor.
Himanshu, our session will going to start around 3,
Okay, sir.
right?
Okay, sir.
Yes, sir.
So we are going to wait for a few minutes, and then at a scheduled time we are going to start. Okay.
Okay, sir. Okay, sir. Thank you.
Okay.
Okay, so now we can start the session. So good afternoon. Am I audible?
Yeah, Himanshu, you are audible. You may proceed.
Okay, okay, sir. Thank you.
Yes,
Okay.
sir.
Okay. So good afternoon to all. I am Himanshu Pachori. Currently, I am working in solar technology, like in solar air heater, with integrated with the thermal energy storage. So and under the guidance of Dr. Tushar Chaudhary and Tanuja Shivade ma'am. And now we will see in this lab session what is how I have designed this setup, and what is introduction about the CFD analysis and mathematic modeling, and also I will explain the experimentation part, how I have conducted this. So now we can start with introduction session. Okay, the screen is visible.
Yes, sir.
Is it visible?
Yes, sir.
Okay, thank you. Now I start with introduction part. Mainly, first of all, the energy is a very crucial source of developing nation. So now we have to first of all maximum utilization of the solar energy is a very necessary part, as we can listen from the previous lecture. The a lot of introductory and very nice presentation related to this field. Now I am slightly introduce what is the effect of solar radiation in our earth and in our society. So we can the solar radiation highlights the broad potential of the solar energy for various thermal and electrical application. The solar spectrum, as we can see from the right hand side, the ultraviolet radiation through visible to infrared wavelength shows the significantly higher radiation outside the Earth's atmosphere compared to that at sea level, due to the atmospheric scattering, absorbing, and reflection part. Despite these losses, the substantial portion of the solar energy will reaches to the earth, and it is reliable to utilize in our renewable source of energy, convert into the electricity part and the thermal part to utilize in a different application, like drying a domestic water heater, as shown in the figure, in electricity as we know, and solar thermal application, heating, room heating, cooling, etc. So the wavelength ranges from the 300 nanometer to the 2500 nanometer, carries the majority usable of solar radiation. Okay, and the classification of the thermal energy storage basically depends on, we can integrate it with our solar thermal setup, like a sensible heat storage, basically a sensible and latent, and other type also are liquid gas detection, chemical store in it's with respect to an chemical storage, liquid gas reaction, solid gas reaction, gas reaction. So nowadays the research mainly focused on the latent and sensible heat, and uh, the research motivation, as we can see from the figure, the energy use, the distribution across heating, cooling, transportation, power, along with annual CO2 emission, as we can see that the CO2 emission increasing with increasing the year, day by day also, we can say, or year by year. So the largest share of the energy used, the 51% in the heating and cooling, as we shows in the figure, with renewable energy contribution approx 9.8% only, and supported by the 8% from the modern bioenergy and solar thermal, geothermal resources. However, the 5.3% still comes from the non-renewable and electricity, showing slow progress in decarbonizing this sector. The transport sector, representing the 32% of the energy uses, uh, which is heavily nowadays heavily depends on the fossil fuel, but now it is converted in electric side also. And we can see the renewable energy 3.3% approx, and 3% from the biofuels. And 26% of supply coming from the renewable electricity, and highlighting it is significant advancement in clean power generation. And we can see the tons of emission CO2 increasing nowadays in as well as developed and developing countries also. So basically, motivation behind it to having a low or no emission of the carbon, we will also contribute this energy to maximum utilization of the solar to reduce our CO2 emission and global warming, etc. And the solar air heater, mainly I have focused on this device. It is basically application at different type of space heating, drying farms, timber seasoning, paper mills, natural butter, and so on. Basically, it is a non-polluting and renewable based energy. The types of solar air heater we can see from the figure. The basic type is the single pass and double pass solar air heater. The solar heater generally consists of an absorber plate, as shown in figure, with a parallel plate below, forming a small passage through which the air to be heated flows. As in the case of the liquid flat plate collector, a transparent cover system is provided above the absorber plate. While the sheet metal contains are filled with the insulation is providing on the bottom side. In double pass, we can say more advantages as compared to a single input, because of there is less emission of the uh, less emission uh, less loss of energy due to the double pass. And in single pass, mainly losses from the upper side, glass side, heat energy. And in double pass, one more benefit regarding, we can fill the thermal storage, because of we have more space as compared to a single pass. And due to the double pass, we can collect the more energy as compared to the single pass. Okay, so now comes to the concept of artificial roughness. Why artificial roughness comes into the contact with solar air heater? Because of the main part of the solar heater is the absorber plate, and the absorber plate have different type of as we can already previous lecture delivered the number of absorber plate is here. So I have worked on our artificial roughness based absorber plate. The basic concept of the roughness is to increase the turbulent effect as the vicinity of the absorber plate. Because of, if there is no roughness is there, so therefore, we can see in figure viscous sublayer formation will be there, and it is a obstacle to transfer the energy from the absorber plate to the fluid. That's why we have a low efficiency and low temperature difference between the absorber plate to the air, and that's why we have to develop the artificial roughness. But it artificial roughness to increase the effectiveness, heat transfer effectiveness from the absorber plate to the fluid. Okay, and so that's why we have to manage the design of the absorber plate. It is basically depends on the pitch artificial pitch. Pitch means the distance between two roughness and relative roughness height parameter. In next slide, we will explain it. First of all, pitch, the relative roughness pitch plays a crucial role in the design of the design of the absorber plate, because of we need to justify or specify the reattachment point. Okay, so if there is a no reattachment, so it is it is obstacle to transfer the energy from the absorber plate to the fluid. So it is need to develop the reattachment point and fix the parameters of the P by relative pitch relative roughness pitch. That's why at this reattachment point, there's a maximum energy utilization from the fluid from absorber plate to the air. And second one is the relative roughness height, E by dH. So the height of the roughness is also plays a crucial role. So if we can if we can we will not optimize the roughness height, so there is a enhancement of the pumping power and losses of energy. So it is necessary to optimize the height of the roughness, and angle of attack also importance role, because of the angle of attack specify the at which angle air flows over the absorber plate. Okay, so now move to the workflow charge. First of all, there is a material selection of the absorber plate and the material of the roughness, and at which the insulation material. There is different type of material I've used. The design parameter like roughness design, design of the the setup, and then CFD analysis, which is validated from the researcher, and validate the how and optimize the roughness, how at which roughness it will gives the good performance. So it is very necessary to do the safety analysis, then move to the design and fabrication part, and then apply to the experimentation on it, and performance analysis based on energy, exergy, etc. To with thermal storage and without thermal storage, and compared both of them to, at which have specify the good performance. The mathematic modeling of the and CFD analysis of the solar radiator. First of all, we have specified the number of absorber plate. You can see the V-shape absorber. I have chosen the V-shape absorber plate because of it has a from the literature survey, it has a good transfer, good develop the good turbulent effect at the vicinity of the absorber plate, and transfer the energy. But we need to optimize the parameters like width ratio. The W by W specify the width of the absorber plate and the width of the V-shape roughness, first V. Okay, so there is a number of V-shape roughness is here. So with the help of mathematical mode, there is some equation of Nusselt number and friction factor is here to perform it with the help of this flow chart in MATLAB. And also after this analysis, the thermal storage, CFD analysis will be performed after the mathematical modeling. So there is some governing equation, right? The radiation transfer equation, continuity equation, momentum equation, energy equation will be utilized to in a CFD analysis to perform perform the CFD analysis in the solar radiator. And these are the setup, CAD model of the setup which I have developed in our lab and SETA lab. There is we can see the blower, which is suction blower, have been used in a double pass solar radiator. I have utilized a different type of absorber. There is mentioned only one type of optimized absorber plate. I have used a number of without storage experimentation of without storage and with storage, both absorber plates. So parameters and boundary conditions of the solar air heater. The parameter has specified the 1300 to 30, which is the length, width, and height of the setup, and the mass flow rate, different type of number of mass flow rate I have utilized the in emissivity and of the absorber plate is 0.9, and the parameters regarding I've used in CFD the inlet condition, the velocity ranges from the 0.8 to 4 meter per second, and the outlet 4.6 meter per second, and the outlet condition is zero gauge Newton per meter square gauge ratio, and transparent glass is utilized, and DO discrete model used for radiation, and the pressure velocity coupling at used in a simple ski, and number of mesh iteration approx 40 lakh is used, and the paraffin wax, the detailing of the thermal storage, I have utilized the paraffin wax is OM organic material OM48, which has melting temperature is 48 degrees Celsius, and the latent heat of fusion is about 1,72,000 kilojoule per Kelvin, and kilojoule, and density is 875, and thermal conductivity about 0.2 watt per meter Kelvin. This is the temperature contour of different roughness of the absorber plate, which I have utilized 1, 4, 6, 8, and 10. We can see at this different temperature zone is there, and different contours which is shown in the absorber plate. So we can see the rough without roughness, smooth absorber plate, the high temperature, but there is a transfer the energy from absorber plate to fluid is very less as compared to the roughened parameter. So in further analysis, we can specify the what is good for our absorber for our setup. There is some the grid independent test and comparison of the radiation model. Different type of radiation model have used DO model, Roseland model. The DO give the good performance as compared to the Roseland model. The governing equations, the enthalpy porosity is method used for the PCM to analyze the melting point to the solidifying, and what is the zero is regarding to the melting, and one state for zero is for stand from the liquid, and solid for solid, and one stands for a liquid phase. So with the help of this method, we will analyze the performance of the PCM. The liquid fraction of the PCM, as we can see, different starting there is a solid phase, and after 2 hours of the heating of from the artificial radiation, because we have used the artificial radiation at 1000, we can also manage it with the help of regulator to reduce or maximize the radiation. So this is for 1000 watt per meter square. The liquefaction after in 2 hours, there is a gradient of color. We can show the liquefaction starts solid to liquefy, and after 2 hours, it is completely liquefy in nature because of the thermal storage uh, in latent, based on the latent heat storage, it gives the store the energy, and we can use the after sunset. So we have switched off the artificial radiation mode, and utilize at how much time we can use this storage energy after after the sunset, or we can say after the switch off of the radiation. And this is the temperature regarding temperature contour, so, and regarding the width storage in a solar air heater. we can see approx 322 Kelvin temperature is reached, maximum temperature of the PCM, and absorber plate also. Sorry. Okay. This temperature contour shows depends on the temperature gradient with respect to the different mass flow rate, or we can say the different Reynolds number at 4,000, 10,000, 6,000, 12,000, and 8,000 and 16,000. A different mass flow rate, I have utilized what is the effect of the temperature in and what is the utilization of the temperature from the absorber plate to the air, and uh, the maximum storage efficiency with the help of CFD analysis. In this contour, we can see the reattachment of the fluid. This is a velocity contour of the solar air heater. The reattachment contour, breaking of the viscous sublayer, we can see there is a maximum heat transfer rate from the reattachment of the fluid to the air. Due to this CFD analysis proved that at this geometry, W by W equal to 6 give the best performance as compared to the other uh, to uh, to breaking the maximum viscous sublayer and maximum heat transfer rate from the absorber plate to the fluid. This is a pressure drop. We can see the pressure drop also relate importance role in our setup, because we can find out the friction factor and the pressure drop in the system and how much power utilized from the blower. The validation, I have also done the validation with compared to the other researcher also, and experimentation and CFD analysis, which is specify the good relation with other researcher and our experimentation, which is I will explain in further in what is going on in the experimental part. With the help of the CFD and mathematic modeling, I have optimize these roughened parameter, like I have draw the friction factor and Nusselt number graphs as compared with reference to the width ratio 1 to 10, and also compare with respect to the Reynolds number. Okay, in first graph we can see the width ratio equal to 6 give the best performance as compared to the other roughness, and also in Nusselt number shows the maximum Nusselt number in width ratio equal to 6, and in pitch in relative pitch ratio gives maximum for P by E equal to 8 gives the maximum performance as compared to the other pitch ratio. And shows the thermal efficiency. The relative width ratio 6 shows the maximum efficiency with increasing the Reynolds number because of the maximum output energy give the maximum useful energy to the fluid medium, and that's why have a good exaggeratic efficiency also for width ratio equal to 6 also. That's why I have utilized this W by W in the PCM storage in our experimental setup. The THPP, thermal hydraulic performance parameter, shows the different width ratio. The width ratio 6 also maximize the thermal hydraulic performance, approx average equal to increase it with increase decrease with increase the Reynolds number, and average approx 3.0. It is a THPP, actually it is a ratio of the Nusselt number of the roughness to the roughness and smooth plate, and the friction factor to the ratio of the friction factor of the roughness and smooth plate to the power 1 by 3. It is a dimensionless number which shows the performance of the absorber plate. These are the experimental setup in developing phase. I have clicked the photo in developing phase. There's the absorber plate which shows the filled with the PCM, and the converging section where is the outflow of the heat by the suction blower, and the mass flow rate is utilized the experimentation at different mass flow rate and different Reynolds number, and VFD utilize to control the blower to specify the Reynolds number, and to give the performance and experimentation at different Reynolds number. This is a complete setup, which is I have done the experiment. There is a solar simulator. We can see there is the radiation approx 1000 watt per meter square, which is validated by the pyranometer, which is fixed in above the SH setup, and there is a top side absorber plate and bottom side absorber plate also as shown in figure. The temperature sensor which is at the bottom side of the absorber at the top bottom side of the absorber plate, and the thermocouples and the RTD based thermocouple is utilized in our setup, and the whole system is IoT based, which is collecting data uh, direct to our computer, and the humidity sensor also specify the percentage of the outlet humidity in the air. Okay, the in result discussion for the experimental parts, there is I have specify at absorber plate temperature with respect to the time, and at different Reynolds number. There is a increasing graph with time specifies the maximum temperature gained by the particular Reynolds number, and then switch off the radiation and see how much energy gives in temperature to the air, which is utilized in further after switch off the radiation or sunset of the radiation. Okay, so there is a RE 4000 to the RE 16000. There is a Reynolds shows the Reynolds number, which shows the absorber plate temperature maximum temperature shows in low Reynolds number due to the resistance flow over the absorber plate due to artificial roughness is there, and low temperature shows at R equal to 16,000, which is utilized we can utilize as a high mass flow rate, and at outlet temperature we can see a different Reynolds number shows the different outlet temperature. There's a maximum temperature approx 53 approx 52 degrees Celsius for roll Reynolds number, and at high maximum Reynolds number 16,000 shows approx 42 degrees Celsius, and after switch off the radiation, the melting stage of the PCM is converted into solidify, and the extract the energy from the absorber plate to the fluid medium. That's why we can also utilize approx 4 to 5 hours after the switch off the radiation. Similarly, if we experiment in the open air, so we can after sunset we can utilize approx 3 to 4 hours of the energy from the solar air heater in different applications. The PCM temperatures in charging and discharging mode shows at different Reynolds number. There is a maximum 4000 Reynolds number shows the maximum 64 degree approx 64 degrees Celsius, and minimum for higher Reynolds numbers approx 55 degrees Celsius at the 16,000 Reynolds number. In discharging phase we can see the we can see the maximum temperature after discharging gives the low Reynolds number, and minimum temperature uh, uh, as shown in higher Reynolds number. Okay. In next figure shows the Nusselt number and friction factor uh, moves with respect to the Reynolds number, and this shows the RE 4000 and 16,000. It shows the 16 and 155 Nusselt number respectively, and the PCM and roughness duct indicating the enhancement average approx 120% as compared to the smooth duct. When we compare with the smooth duct, it is about 130% enhancement, and indicate uh, uh, it indicate this primarily due to the effect of V-shape roughness, rifts, and angle of attack that induce the in a turbulent mixing, and latent heat absorption capacity of the PCM that maintain the higher thermal gradient across the absorber surface. The PCM and the roughness duct indicating average decrement of 49% compared to the smooth at Reynolds number 16,000. And we can see the comparison, the thermal efficiency of the system. This is for 1000 watt per meter square artificial solar radiation, and the higher Reynolds number gives the best thermal efficiency, approx 92.3% approx, and this indicates the higher mass flow rate and hence the turbulent effect by the artificial roughness near to the absorber plate, and ribs configuration which is breaks the viscous sublayer and creating the free flow. Hence, the greater convective heat transfer coefficient to the transfer to the energy to the air, and at a lower mass flow rate, approx 4,000 to 6,000 Reynolds number exhibit the lower thermal efficiency, approx 30 to 45%. After reaching the maximum efficiency of all Reynolds number curves at quasi state phase, there is heat storage PCM, and PCM after flatten of the curve, the switch off of the radiation, the flatten curve shows the reduction of the efficiency, shows the switch off the radiation, and shows the efficiency after the discharging phase. In second graph shows the comparison of the thermal efficiency with compared to the without PCM and smooth duct, which shows the sorry, with the roughened duct achievement 34% thermal efficiency at R equal to 4000, and smooth duct yield at same Reynolds number approx 19%. At higher Reynolds number, the roughened duct shows the 92.3% efficiency, and similarly the smooth duct shows the 40% efficiency, which shows the R setup with PCM and roughness gives the better much more efficiency as compared to the normal conventional solar aerator. And this is show the exergetic efficiency. The exergy efficiency basically means the maximum useful energy utilization from the from the air and deliver to the application part. Okay, so this is a second law of thermodynamic, second law efficiency. We can see at it shows the thermal efficiency peaking range approx 9 to 11 at 4,000 to 6,000 Reynolds number, and maximum it shows approx 21% for 12,000 Reynolds number. And with compared to the smooth duct, we can see that there is a much more exergetic efficiency of the with roughness and PCM. And also the right hand side graph shows the exergetic efficiency at different types of different Reynolds number with respect to the time. And the heat storage, we have specified the heat storage with Reynolds number. The heat storage with charging heat, discharging heat at with respect to the charging time and discharging time shows in figure. So the PCM stores its maximum energy at lower mass flow rate exceeding 130 to 140 kilojoule, and after at higher Reynolds number is fall below the 16 or only 60 kilojoule because of cooling of the at higher mass flow rate cool the absorber plate and solidify the PCM material. And in THPP, we can see thermohydraulic performance from the experimentation. It shows the higher at approx 6,000 Reynolds number and lower at 12,000 Reynolds number for the thermal hydraulic performance parameter at different Reynolds number. So this is now the experimentation CFD parts of the our setup. Now, in social impact of this, the dry agriculture products like grains, fruit, vegetables, as well as seasoning food. In winter, solar heater are used to heat a house and save the energy. It is also a non-polluting and renewable energy sources. So these are the some references I have used in our research papers and in our slides. Thank you. For if you have a question, so you can ask.
Himanshu ji, you have taken PCM,
Yes, sir.
aluminum oxide, I think, right?
Uh,
You have
no,
taken your
sir.
PCM, energy storage as aluminum oxide, no? Sure.
No, sir. No, sir. I'm not doping any nanomaterial. Only a
Energy storage PCM, this PCM is aluminum oxide. No, this is paraffin wax, right? Without
yes,
any
yes, sir.
material. Okay.
Without any
Without any
liquid.
okay, it was paraffin wax, right? With melting
Yes, sir.
temperature 48 degrees centigrade, I think so.
Yes,
And
sir. Yes, sir.
so, is there any reason behind selecting this particular PCM?
Yes, sir. Because of the paraffin wax also shows the at a low temperature zone because of the solar air heater mainly utilized in a low temperature zone below the 100 degrees Celsius. At 48 degree, we can easily melt at the solar radiation in when we experiment in the open environment. I have also experimentation of the PCM in open environment. There is easily melt at 1,000 or below approx 800 and 900 watt per meter square radiation, and they store the energy after the melting.
1000 watt per meter square was your radiation, and you have applied for 2 hours, right now?
Yes, sir. Yes, sir.
You had applied 1000 watt per meter square radiation for 2 hours, and you had completed your experimentation. Am I right?
Yes, sir. Yes, sir. Yes, sir.
Okay, so
At
only
different
for the 2 hours, time it was charged, and then after how much time you had taken to discharge?
uh, approx at depends on the mass flow rate. If we can see the at lower mass flow rate, at discharging time approx 4 to 5 hour we can utilize the energy after discharging phase.
Actually, yeah, in terms of the mass flow rate, if we talk, or in terms of the Reynolds number, we talk, it is the same thing, no? What I
Yes,
understand.
yes, yes, sir. Because I have calculated the Reynolds number from the mass flow rate. I have I've
Okay,
also
okay,
shown
okay.
the table of Reynolds
In
number and velocity.
in the
These are
simulation, during the simulation, you may have done in any way. Here, the Reynolds number you had taken 2000 also, but in your results, you had not discussed about the 2000 values at the Reynolds number 2000, because you have always in all the graphs. I think Reynolds number was
yes,
started from
yes.
4000 adwards. Is it?
No, yes, sir. I actually used the 2000 in the without PCM, and in PCM I started from the 4000 because in 2000 there is a very there's no effect in PCM. In without PCM we can I have start from 2000 to 18,000, and with PCM I have utilized 4000 to the 16,000 because benefit.
1 minute, 1 minute. Actually,
Yes,
I
sir.
wanted to know when the 2000 Reynolds number was there.
Yes, sir.
2000. What was the mass flow rate?
Uh, approx
Mass flow rate of
mass
air, na? This Reynolds
uh,
number for the air, na? So what was the
point
mass
is
flow rate?
yeah, this is 0.008 kg per second.
So it was possible in your experimentation experimental setup to control this
Uh,
mass flow rate, na?
actually, yes, approx, because our experimentation blower start from approx 3000. That's why I have utilized in simulation only, approx 3000
In
to
the
18.
simulation, and during the experimentation, it was difficult to achieve this.
Yes, sir, yes, sir. So that's why I have started from 4000 because 2000 the turbulent also start from after the 2000 because our setup designed for only a turbulent effect of the air. So after 2000 it is beneficial to in experimentation. In additionally, I have see the what is going on in 2000 also. That's why I have
So it was included in your experimental setup to measure the mass flow rate of the air at the
yes, sir, yes, sir.
outlet
Yes, sir.
also.
Uh,
Okay, nice,
yes, sir,
nice.
yes,
It
sir,
was
yes, sir. Yes, sir. This setup shows the outlet mass flow rate from the mass flow rate meter.
okay. So the same mass flow rate will be. So it was only with the mass flow rate you have controlled the whole Reynolds number, right now?
No, no. From the mass flow rate, I have calculated the Reynolds from the mass flow rate, and mass flow rate converted into the Reynolds number. But I have controlled with the help of this VFD. This is a VFD variable frequency drive, which is control the blower, the speed of the blower, speed of the fan.
Speed, instead, we may have the rotameter to check the speed and then after to have the control over this. Is it so?
Actually,
So you are having the
no,
variable frequency.
yes, sir. VFD have already electronic device automatically control the frequency of the speed.
Okay. Of your blower. So you can
Yes,
control the
yes.
flow rate accordingly and
That's
you
why
can.
the fan speed is regulate. As we can see in our fan, the control regulator is there, so we can control 1, 2, 3 mode. So that's why similar phase in three-phase blower
Okay, but
with the help of VFD.
okay, this thing is very clear to me. You have changed the Nusselt numbers also from a particular range to this particular range,
Yes, sir.
and
Yes,
the graphs have been run. So
yes, sir. Yes, sir.
how this Nusselt number was changed?
Actually, Nusselt number directly related to the Reynolds number. If a Reynolds number changes, the Nusselt number also changes.
Okay.
Yes, sir. With the help
For
of
for,
HL.
for the given
Yes.
for the given value of Reynolds number, this was the Nusselt number. So
Yes, sir. Yes, sir. Because
no
the heat
separate.
transfer coefficients also change. HL by basic formula of the Nusselt number is HL by K. So H
Yeah.
is depends on the mass flow rate. This mass flow rate is changing. Reynolds number is changing. The H is also changing.
So for our result purpose,
Yes, sir.
either we talk about the variation of the only Reynolds number, or we may talk about only Nusselt number. But we have to,
No. Yes.
in a particular graph, we have shown a variation of Nusselt and Reynolds both separately. I think so. It was
Uh,
there in a particular graph.
yes, sir. Yes, sir. In experimental graph, I have shown.
So
Uh,
no, I was just, I want to ask, and so that I could understand the things, how to control both things separately by heat transfer, addition of the heat, because it is conduction and ratio of the convection and conduction, HL by K, no, as you said.
Uh, no, sir. Actually, Nusselt number directly depends on the Reynolds number. That's why it is in y-axis and Reynolds number in x-axis. And when we change it, so at higher Reynolds number, it shows the increment or decrement of the Nusselt number with respect to the graph. And because of the heat transfer, Nusselt number actually shows the heat transfer rate from the absorbed plate to the air. So directly depend on the mass flow rate.
Nusselt number is a function of Reynolds and Prandtl. If it is a particular force
Yes, sir.
convection.
Yes,
If
sir.
it is a free convection,
Prandtl
then
number.
Nusselt is a related function of Reynolds and
Yes, sir.
Grashof number.
Yes, sir.
So as we
Yes,
know
sir. Yes.
fundamentally, so
Yes, sir.
if Nusselt number is a function of not only the Reynolds number, also the another number. So that's why you have drawn this curve, because both are independent variable. I think so.
Yes, sir. Yes, sir. But I have also mentioned the Prandtl number because it is actually a fixed parameter, 0.7 for air. So that's why only we have an option to variable the Reynolds number. So that's why we have shown the Reynolds number with respect to the Nusselt number graph.
Also, Himanshu, one more thing which I observed, because it is a very common while getting the results. When it is
Yes,
the
sir.
simulation, then
Yes, sir.
it is easy to get. When it is experimentation, then the things are very difficult. If you come to the later slides, as we have
Yes, sir.
observed, the results shown, no, later on, results shows that when PCM's performance without PCM, with PCM, you have showed in the last slides. And one more. Yeah, I think
This.
it was the bar chart. Just move further. Move further. I think last you have drawn because with PCM and without. Yeah, this one. I think 35. Slide number 35. But
Yes,
it
sir.
is a very smooth curve, no? Just come later. And I think after 38, is there anyone? Slide number after 38, 39. No,
After
just
38.
move further. No, it is not there. Okay, you can see in the slide number 38. Because,
38.
okay, just this slide I wanted. Yeah, thank you.
This, yes.
This one. Actually, exergy efficiency was given, and it was
Yes, sir.
very uncommon to see. In another graph, also bar chart, I had seen when the Reynolds number is 11,000, I think it was earlier 10,000. In another graph you had shown earlier, I had seen.
Yes, sir. Yes, sir.
The thing was not very smooth. Here is in this particular exergy efficiency versus Reynolds number. You see, at the 8,000, it is going higher, right? 6,000 very
Yes, sir.
low, 8,000 very
Yes,
high.
sir.
Okay. If the trend is to increase, so let it be 10,000. It is getting decreased. Again, on 12,000, it is increasing. But 14 and 16 are again taking. But 14, 12 to 16, a systematic fall down is there, right? But
Yes, sir.
before
Yes, sir.
that, abrupt change was there observed at 10,000. So, what you have observed? Is there anything special you have observed, or maybe this nature of the results we obtain?
Actually, this nature of result I obtain, I think the mainly the PCM melting temperature and solidification and melting of the PCM also plays the important role in this zigzag pattern. So in without PCM, we can observe that there is increment slightly or decrement of the exergy efficiency. But with the help
Yeah,
of
it is there. Without PCM, no problem, because it was a smooth
yes,
curve.
sir.
But
Yes,
with
sir.
PCM, this abrupt change was there. So when a PCM is getting melted, no, because of its chemical,
Yes, sir.
so you might have taken the lab specimen. I think PCM from any chemical industry, no, which gives you
Yes,
the
sir.
very specific for the lab purpose.
Yes, sir.
So from
Yes,
where
sir.
we have taken this PCM, paraffin wax.
Uh, Actually, this company is 1098. I have purchased from the paraffin wax.
Oh, Indian.
Yes, I think India. Yes, sir. Indian. 1098. It is office also in Chennai. 1090.
Okay, so I need to have the address of this particular, because sometimes for our own purpose we
Yes,
need
yes,
this
sir.
paraffin waxage, but
Yes, sir.
sometimes we don't get this 48 degrees centigrade melting temperatures in commonly.
Okay,
I belong to the Allahabad, and it was difficult for me to purchase it locally, so that's why I was
okay, sir.
asking these related questions.
Okay.
Okay,
Okay, sir. I
Himanshu.
will also share the address of
Yeah.
this because I have purchased from 2 to 3 companies. 1090. One more company is there. So I will share through the mail from which I have and also a quotation and other related thing of the PCM.
Okay, so another graph like this bar chart, it was the exergy efficiency, maybe the thermal efficiency. If chart is there, if you, yeah, that's this. Oh, just one. Be back.
Yes, sir.
Last slide you have shown. Just come to the last slide. I
Last
think
slide.
this one is there. No? This one is there. Okay,
This
just
one.
1 minute. In the case of THPP, but on some
Yes, sir.
another I had seen earlier. 8,000 lower, 10,000 higher, again 12,000 lower. But this may be due to the PCM, as you said me.
Yes. Yes, sir. Yes, sir.
Maybe the case. Okay.
Yes, sir. Yes, sir.
Nice, because since it is a FDP, that's why I asked everything to you. Else
Yes, sir.
otherwise I
Yes.
could not have asked, because it will certainly enlighten me for the experimental purpose also.
Yes, sir.
For
Yes, sir.
the simulation purpose, you had used softwares, and it is available in your
Yes.
library.
In experiment, there is a multiple factors, environmental, also melting solidification, a different zone is also matter on this R setup. So that's why this changes is here.
In the morning session, some experts have also talked about this nanoparticles,
Yes, sir.
and
Yes.
it was common to use the aluminum oxide nanoparticles. But when we
Yes,
use
yes, sir.
it is not uniformly getting distributed, and some problems we have observed several times. So
Okay,
unfortunately,
sir.
I started to talk about the paraffin, and
Yes, sir.
I
Yes, sir.
started with the aluminum oxide, but I was somewhere else,
Yes, sir. Yes, sir.
and we had. Okay, thank you, a lot of thanks, Anshuji.
Okay, sir. Okay. Okay, sir. Please drop the mails. That's why I will share the all the details of the PCA.
Okay,
Okay, sir.
thank you.
Okay. Thank you, sir. Mhm. Okay, Aman.
Okay, so thank you so much, uh, Himanshu, for your such a nice presentation on the thermal energy storage and solar air heater. And yes, obviously, those who are working in this direction will be benefited by the information you shared. And with this, we are having one more session at 4 p.m. So we can wait. We can take a break of 8 minutes, and at 4 p.m. we are going to have our session from uh, a a very well-known personality from IIT Tirupati, that is Professor P. MuthuKumar. So we can wait for 8 more minutes, and then we will be starting the next session. So good afternoon again, everyone. And I just received a message from Professor MuthuKumar. He is joining. He's trying to join. There may be some problem uh, with his hand, so we can wait for 2 or 3 minutes more. Yes, so again, very good afternoon to everyone. Our eminent guest has joined the session, and before he started his session, I should introduce him. So, we are very fortunate to have the personality from IIT Tirupati, Professor P. MuthuKumar. So, Sir has received his PhD degree in mechanical engineering from IIT Madras in 2005. Then he joined IIT Guwahati as assistant professor in January 2006 and became professor in January 2015. He joined IIT Tirupati as professor in mechanical engineering department on 2022. He received DAD Research Fellowship, that is DAAD, during September to December 2000, then June to July 2008, and June-July 2010. He is the recipient of IEI Young Engineer Award in 2010 in Mechanical Engineering from Institute of Engineers. He has received Bhaskar Advanced Solar Energy Fellowship, that is BASE Fellowship, from Indo-US Science and Technology Forum, that is USIEF, in January 2014, and also received Engineer MP by a National Award 2015 from by the Institution of Engineers, Udaipur. He is also the fellow of Institute of Engineers, India, and he is one of the commission member of to represent India in the International Institute of Refrigeration, that is IIR. He also received the Fulbright Nehru Academic and Professional Excellence Fellowship from USIEF, that is in 2018. He has served as the president of Indian Society of Heating, Refrigeration and Air Conditioning Engineers, Guwahati subchapter. He also received Mechanical Engineering Design Award 2017 from National Design and Research Forum of the Institution of Engineers on 2017. During 2019, he was honored as the eminent engineer from the Institution of Engineers, Assam State Center. If I talk more about him, then he appeared in the world's top 2% scientist published by the Stanford University USA report. He has won Birak Innovation Challenge Award SOCH 2020-21 for Stage 1 and Stage 2. He was honored with an award of Outstanding Engineering Service to Country by the Constitution of Engineers India, Rajasthan State Centers on 2021 to recognize his outstanding contribution in the field of thermal science and energy technology, as well as his contribution in the growth of country's engineering profession. He has been awarded for the prestigious Abdul Kalam Technology Innovation National Fellowship 2021. He has published around 350 research articles in various international journals and conference proceedings, edited 4 books, and written 16 book chapters. He is having 12 national patents for his credit, and he served as guest editor for 3 Elsevier Journal special issues, including Elsevier and other reputed journals. He has supervised 24 PhD, 65 MTech, and 5 MS students' thesis. He has successfully completed 10 sponsored research projects worth 6 crore and 50 lakhs rupees and 5 consultancy projects worth 75 lakh rupees. Currently, he is handling 7 more research projects worth 12 crore. He is the reviewer of more than 75 international journals in the area of hydrogen energy, energy storage, refrigeration, heat transfer, and received several research proposals from DST, MNRE, Qatar Research Board, etc. He has been serving as an expert in several ministries, including DST, MHRD, Ministry of Oil and Natural Gas, Ministry of External Affairs, etc. He is also expert committee member in BIS, AICT, NAC, and many other professor organizations. His area of research includes sorption heating and cooling systems, hydrogen energy storage, metal hydride based thermal machines, coupled heat and mass transfer in porous medium combustion, etc. If I talk more about, then it would not end. And I am very fortunate to have this eminent personality in our FDP, and we are very grateful because sir will enlighten us in the direction of the advanced thermal technologies and with his great knowledge. And so I heartily welcome Professor P. MuthuKumar from IIT Tirupati.
Yeah, thank you, Dr. Tushar.
Aman, sir.
Isn't it your name, Tushar?
Sir,
Yeah.
is Dr. Raman, my research associate
Okay.
over here. So, sir, I am Dr. Tushar. I am first of all thank you for accepting our invitation and being a part of as a resource person for this FDP. So it's a great privilege for us to be a part of to this FDP over here, and we are going to be enlightened by your words over here. So the screen is on yours. So you may start, sir.
Yeah, thank you very much. And sorry for the inconvenience. There is some technical glitch in my laptop.
No
I was
problem,
trying
sir.
to join in the other system, but unfortunately, it's not allowing the Zoom to open. That's asking so many details. That's why I joined from my laptop. Anyway, so you can see my screen. So without wasting much time, I will let me.
I think there is some technical glitch. Sir, are you there? Okay. He's joining again. So please wait for a minute. There is some technical issue from server. So he's joining very soon.
Hello, are you able to hear me now?
Yes, sir.
Yeah,
Now it
sorry,
is. Yes, yes.
some issue in the
No issue,
Wi-Fi
sir.
network.
No
So I will
problem, sir.
join now. Join my data, mobile data. Now,
Sir.
you able to see my screen now?
Yes, sir. Yes, sir.
Okay, fine. So the presentation is visible. The presentation is visible now.
Yes, sir. Yes, sir.
Okay, fine. Let me get in my. Okay, so the topic what I have chosen for this FTP is the the energy efficient, environment friendly porous turbine burner for cooking and industrial application. So before that, just I wanted to give you a small brief about the SDG, Sustainable Development Goals. There are about 17 Sustainable Development Goals. Most of you are aware of all these things. Most of the developed and developing nations are committed to achieve these 17 goals before 2030. Among these 17, the sustainable goal number 7, energy. Okay, that is energy that is providing clean and affordable energy. Basically, this is stand out to be the prime one. So that means once you achieve the sustainable goal number 7, then only you can achieve the remaining one. So therefore, the energy is given due importance, across the nation. When you talk about the energy, all the basic human needs, whether it is a food or making shelter or cloth or getting a fresh water, everything, without energy we cannot do anything. Even in future, it may so happen that we need to spend energy for getting purified in a year. So basically, in each and every activities of the human being, or maybe this one, energy is associated. So when you talk about the sustainable future energy, it should be reliable. That means it should be available at any point of time. It should not create any danger to the population, and price should be reasonable. And it should not create any, impact. That is the unacceptable impact to the environment, and it should be available for the long term. These all are the, the various requirement of the, the sustainable energy source. So this is the current energy scenario, though the information is little old, I think about 8 months, but more or less the trend is same. So right now we have roughly about 5 lakh, if you see the latest one, 5,80,000 megawatt installed capacity. Most of them, around 50% are from the fossil fuel, and remaining renewable is roughly about, if you include, you can say the hydro. So the renewable is roughly about 50%. We are of course much healthier than the world average. So if you compare these three forms of energy, whether it is a fossil or renewable or nuclear, and the fossil is of course safety wise it is fine. The major penalty here is the CO2 emission is the major penalty, and cost is the moderate. And coming to the nuclear, again the waste disposal is a major concern. Otherwise, the technology is fine, and you can say safe, except the waste disposal. Availability is unlimited. Now coming to the renewables, here it scores in all aspects. It's a clean and available, abundant, and safety is very high. So here there is no kind of a concern of safety or anything. The cost has come down now. If you go with without storage, even you can generate one unit of electricity at a cost of about 2 rupees 30 paise. And now coming to the energy scenario globally, around 30% of the population do not have access to the electricity. Still, this is a concern number. And among all these things, the another the big concern is the cooking sector. Around 40% of the world population do not have access to the clean cooking fuel. As a result, you can see there is a tremendous death is being recorded in this sector. Even in India, we are losing nearly about 3 lakh people every year, mainly due to the improper cooking practice. So to counter this, to answer this, the scenario, so now the government is promoting the clean cooking fuel in several forms. And again, the world also taken the serious concern about this, cooking side. And they are also trying to implement the several solution which is sustainable. Now coming to the Indian perspective, so we use LPG predominantly for cooking application. Now we are exercising the other options such as methanol, ethanol, even hydrogen also being explored, but it will take some time. But if you see this one, we are not self-sustained in terms of the LPG. Almost 50% of our LPG requirement is being imported. As a result, we are spending roughly about 40 to 50,000 crore mainly for LPG import. And by 2030, our government is planning to cut down the LPG rate by about 15 to 20%. So, and another scenario, if you see this one, the increasing LPG demand every year. I mean, every year you can see roughly about 8% it is increasing, and LPG consumer also it is increasing steadily. Right now, we have 33 crore LPG consumer in the domestic sector. And maybe if you see this one, this number also going to be, increase in the upcoming years. And similarly, we also have, significant amount of consumption in the industrial sector as well. So these are the various cooking options available for, available for us. The various types of, burner like Nikista regular burner, slide flame burner, sun flame burner, etc., etc. Like this, we have several one. Most of these burners efficiency are roughly about 60 to 65% efficiency. This is the you can say the energy utilization efficiency, and the most of the burners are having high emissions in terms of CO and NOx. So none of these burners fulfills the requirement of the World Health Organization. So basically, this burner works on free flame combustion. The LPG is injected through the nozzle, and at the exit of the nozzle, since the low pressure is created, the natural air will entrainment. Natural air will entrain, and when it passes through the mixing tube, you can see here there is a tube, and it get air and fuel get mixed, and when it reaches the top of the burner, it get combusted. So you can see the flame. So it's a free flame combustion. So there is a standard 4246, which defines the thermal efficiency, basically which provides the specification of the domestic burner and also defines the performance of the burner. Here the performance of the burner is, you can say, tested or maybe estimated by conducting the standard water boiling test. So you have to take a aluminum vessel of a required diameter and take about 8 to 10 liters of water. This quantity of water varies from power rating of the burner. Then heat the burner from atmospheric temperature, say 30 degrees Celsius up to about 90 degrees Celsius. During the heating process, the enthalpy gained by the water along with the vessel is the output. Like you can see here, MCP of water plus MCP of vessel multiplied by the temperature difference. This is the output, and input is the mass of fuel consumed during this heating process multiplied by the actual calorific value. So this gives the ratio gives the thermal efficiency. Okay. So during this process, the vessel need to be, it should not be insulated, and it should be exposed to the atmospheric temperature in the range of about 28 to 30 degrees Celsius. So as per this protocol, if you see the thermal efficiency of the best available burner, domestic burner, ranges from 68 to you can say 60%. So when the burner is operated at high power, the efficiency will be about 60%. Similarly, the efficiency of the burner which is available in the this big restaurant or used in the college hostel, whose efficiency, whose power rating can go up to about 25 kilowatt. If you see those burner, the efficiency will be very low, in the order of about 20 to 25%. And besides having low thermal efficiency, if you see these burners, CO emissions will be in the range of about 1000 to 1200 ppm, and NOx also relatively high. So the CO is basically, it gives it's an indication of the incomplete combustion. That means higher the CO emission will be, the combustion may not be perfect. Okay. And so coming to our technology, so the major concern associated with conventional burner, maybe if you see the domestic one, their low thermal efficiency, high NOx emission, and even the cooking time also relatively high. These are the concerns. So coming to our technology, you can see in the right hand side, it is the this brown color is the, basically our burner is made up of two porous matrix. The brownish color is the silicon, made up of silicon carbide doped with a rare earth metal. Which is highly conducting and radiating porous matrix. It is acting as a combustion zone, and below which you can see the white color line. Okay, the white color line. This is the alumina matrix, which is made up of low thermal conductivity, low, maybe emissivity material. So basically, the alumina matrix is acting as a flame arrestor. Okay, and as well as the preheating zone. So when you inject the air fuel fuel through the nozzle, and because of the low pressure around here, the air entrainment takes place. When it moves through the mixing tube, both air and fuel get mixed, and when it reaches the brownish color combustion zone, it gets combusted. Where physically you can manually combust, like ignite. Once you ignite, and it get combusted. Since the combustion is happening inside the highly conducting and radiating porous matrix, the flame will be submerged, completely submerged. You cannot see the flame. This is a flameless combustion. And since the combustion is happening inside the highly conducting and radiating porous matrix, some part of the combustion heat will be transferred back, through the preheating zone for preheating the incoming air fuel mixture. As a result, the air fuel mixture, before reaches the combustion zone, the air fuel mixture is preheated up to about 150 degrees Celsius. So if the temperature of the air fuel mixture, when it goes above maybe 150 or 160, then the backfire will happen. So you have to be very, very careful. That's why here the design is very crucial. Okay, so by preheating the incoming air fuel mixture and allowing the combustion to happen inside the highly conducting and porous matrix. And here we could get fuel saving up to about 60% in comparison with the conventional burner. And also we could minimize the CO emission by about 85%. This can be achieved by complete combustion of the fuel. So now we are going to see the several prototypes and in fact the actual systems developed. So mostly we are concentrating on the commercial scale systems. For example, you can see here this single one having the capacity up to about 5 to 7 kilowatt capacity. And here we could get thermal efficiency reach about 65%. Corresponding conventional burner efficiency is about 30 to 45%. So here we could get the fuel saving of about 40%, and some cases we got about 60% for the same capacity. Then the cluster, that is the 3-burner, with the 3-burner capacity, we could get savings up to about 50%. And in addition to that, we could also reduce the emission by about 85%. Then, in fact, now we scaled up this system up to about 15 burners. What you are seeing here is the 7 burners. Similarly, we have 9 burners, 11 burners. We had up to about 15 burners, which can have the power output of about 100 kilowatt. These massive burners are used for cooking, preparing food of about 1,000 kg in a day. So such system is already we have installed here in one temple, famous temple, Sri Kalahasti temple, and it's been in operation for almost 2 years. And similarly, the technology also extended for other gaseous fuels such as biogas, and now we are going to adopt it for hydrogen also, and dimethyl ether and methanol, ethanol, many fuel, of course. Now we are. And in the coming to the combustion, so domestic one also we got very interesting results. And you can see here when this was tested almost 4 years back. So this is the 4 years back development. We got about 76% thermal efficiency. Recently, we achieved efficiency of about 82%. And now you can see here the NOx, as per the domestic burner is concerned, the NOx is almost 0. And the CO also we could reduce almost about 1/5 in comparison with the conventional burner. Now we are drafting the BA standard. Once the BA standard is through, and this technology will be implemented for the domestic application. And our burner not only save the fuel, but also save the time. That can be also possible, and you can fine tune. Maybe if you keep the power output slightly lower, and you can get more than 50-60% fuel saving. And if you want to have the faster cooking, yes, that is also possible. In either way, you can have it. So for the domestic thing, we have performed many, experiments, and many dishes have been performed in, parallelly with our burner and the conventional, the best star-rated conventional burner. And this is for a family of 4 members. In a day, if you prepare, the various dishes, our burner consumes about 200 grams of LPG, whereas the conventional burner consumes about 300 grams of LPG. And the time also you can see. Our burner takes only 118 minutes, whereas the conventional burner took nearly about 171 minutes. Okay. So any product, if you want to launch any product to the commercial market, it is essential to do the life cycle assessment. Life cycle assessment in sense throughout the lifespan of the product, not only during the life, and right from the manufacturing of the product. That is the extraction of raw material, manufacturing at various stages, and transportation, and throughout the lifespan of the product, what is the impact created on the environment? Okay, this you need to do it. So we have done this detailed life cycle assessment. There are about 16 environmental mitigation category. So if you see our burner, there is CPRB is our burner. So impact created by our burner on the various environmental fronts are almost 5 to 10 times lesser than the conventional burner. So therefore, our burner is not only energy efficient or environment friendly, but also you can see here in the environment point of view, it is more safe. And so we also extended this technology for the gaseous fuel, the kerosene. This mainly we developed for some specific application, and we have also done for the methanol and ethanol. Already the BA standard is adopted for methanol and ethanol stoves. And again, for the canister-based stoves also with methanol, that also we have developed. This is as requested by the NITI Aayog, we have developed. And our group has published BA standard also for this one. Now, currently, we are working on the development of porous study burner based medical waste disposal and as well as the sanitary napkin disposal unit that is already fabricated and the experiments are going on. And so we have several such applications and many are already implemented. For example, the heater, space heating and drying, and even for the this for dairy industry also recently we have submitted. Pharmaceutical industry we have submitted. I mean we have supplied, and they are working beautifully. Now you can see here some of the these videos. Yeah. So now it is in operation. Now you can see here. I'm also enabling the sound. So it takes, when you ignite, it takes nearly about 30 to 40 seconds to stabilize. Once it is stabilized, then it will become red hot, like electrical. And you can see here now the burner is fully in operation. So there won't be any flame here. The second beauty is that the heat will be directly transferred to the vessel. In case of the conventional burner, you can see the flame will be, of course, it will be completely hugging the the vessel. As a result, the heat loss will be more. But here we could minimize the heat loss to the maximum extent possible, and all the produced combustion heat will be transferred to the vessel through the radiation. Okay. Another, in case of conventional burner, the mode of heat transfer from the flame to the burner is the convection. Since gases are having low thermal conductivity and low emissivity, the heat transfer may not be, that effective. Whereas here, in case of porous studding burner, the predominant mode of heat transfer from the burner surface to the vessel is radiation. Radiation travels at a speed of light. So because of the improved heat transfer, okay, by means of the volumetric radiation, and we could get the savings up to about 70%. So this is the one bigger one we implemented with the this temple. This is in Sri Kalahasti temple, and even this there, in fact, the the cooks in fact first has to make some the burner with a little bit flame also. This is for their convenience. That also we made it with little bit flame. And say anything, it can be modified. You can see here the bigger installation with various things. And they have been we installed this burner in 2023, December, and it's almost 2 years. It's being in operation successfully. And they are preparing many food for nearly about 7,000 people, per day. And so they got, in fact, they reported about some specific cases, the fuel saving went more than 60%, but yearly average, based on their statistics, the yearly average saving was about 40%. Okay. And similarly, this also, we have installed many such installation at various institutes like IIT Madras, Anna University. And recently, last week, I was at Indian Army, Bangalore. They are also given our burner. They are using it. They also reported about 40% savings. And now it's this technology is being tried by several outlets, and the people are very happy, and they are very happily adopting. And so, as I already mentioned, so we also drafted the BA standard for several the fuel, like including the methanol based one, ethanol based one. Many are, of course, the drafted and in the public domain. And this the LERC, this is basically, it's an agency which is governed by the various the oil companies, which again it's a government organization, and they certify the the efficiency of the various burners. And as per their certification, and our burner efficiency is about 62.5 against the the standard one is 45%. That is the best rated one as per the BIS. So against that, we got about 62.5% efficiency. Okay. And many other things are also done. Even cluster burner, we got about 54.8%. Here, the standard efficiency is, you can say, close to about 35% or something. And yeah, this I have the better one. So maybe some of the product for the one. So this is the Kalahasti temple which was taken. So for yeah, you see the second one for preparing the pongal. their conventional burner consumes about 2.2 kg of LPG. Ours is, their conventional burner consumes about 4.5 kg of LPG. Ours is only 2.2 kg. And similarly for the other product also I'm going to show here. So this is the Kalahasti temple. They are given the yearly average one, about 35 to 40%. This is the annual savings average. And recently we adopted the porous sterile burner in our IIT Tirupati hostels. Now we are using only this one. It's been in there for last 7-8 months. And so you can see here against the conventional burner what we have here. Against the conventional burner, our porous PRB and consume almost 73% less fuel. And against the best performing burner, that is the ring burner. There is people call it as a Korean burner. It's the most advanced one. Even the most advanced state-of-the-art burner, against that, our burner consume about 37% less fuel. Okay. So the savings you can see here, the average saving is around, around 40 to 45% across any type of burner. Similarly, IIT Bombay they also observed about 30 to 40% savings, and many other things. Of course, we got it. Even the companies also, some company also reported around 60%, and and so on. This is very impressive one, and so it's a small report from IIT Tirupati. This my couple of my students are working. They have the various types of burner. And the people, really, of course, the cooks and everyone is enjoying, because in case of our burner, when you cook, you don't feel any heat because nothing will come out. All the combusted, the heat which is produced during the combustion of the fuel will be directed to the vessel. So nothing will come out. So the people happily, they can go close to the vessel and work. Whereas in case of the conventional burner, the vessel will be completely surrounded by the flame. So when the people go close to the burner, they feel heated up. As a result, then they will end up with several health issues. So in case of our burner, there is no such kind of the issue. And more importantly, this burner will not produce any soot. That means the vessel never get blackened. Okay. And you can, of course, this will also provides the very friendly cooking. So that means the effort what you are spending for cleaning the vessel will be very less. Okay. So there are several kind of the benefits using this technology. Yeah, you can see here the many are there. And so more interestingly, you can see here for rice cooking, about 60 kg of rice cooking with the ring burner. That's the best rated ring burner. The average consumption is about 4 kg. They have done this experiment for several months. Okay, whereas our burner almost the same quantity, and you see here the time is roughly, this is the best performing burner consumes about 90 minutes, and whereas our burner consumes around 85 minutes. Okay, time is also relatively less, and average fuel consumption is only 3 kg. Okay, now you can see the with best performing one we got about 37% savings. The conventional tube burner, this is the normal burner which is available in almost all hotels and college mess and all these things. Against that, those burner consumes roughly about 5.2 kg of LPG for preparing 60 kg of rice with 250 liters of water, 240 liters of water. And for the same one, our burner consumes only 3 kg. So if you compare with this burner, the saving is nearly about 73%. Okay. And similarly, they also prepared for dal. Dal also almost 55% savings we have recorded. And so they have done, the techno-economic assessment. So the savings, if you see only with our hostel with 1,800 student capacity, the yearly saving will be about 18 lakhs, whereas the investment what these people have made for this burner is less than 6 lakhs. Okay. And almost you can get 3 times of your investment as a profit. Maybe if you leave the investment, 2 times of your investment as a profit, net profit. And if you see the CO2 reduction, when the technology used, the amount of CO2 reduction will be roughly about 1,500 tons of CO2. That is a huge. And even if you take the CO2 at bare minimum rate, carbon credit, the $3 to $4 per ton of CO2, this will be huge. Okay, that will be almost equivalent to your fuel. And by 2029, because our campus strength is going to increase by about 40% increase in students, and we are going to become 3,000, which is already approved. Then with that, then the fuel saving, it may go up to more than beyond 25 lakhs. This is only for one institute. And so if this technology is implemented across the India, the savings, in terms of the fuel savings by the government of India, it will be, very huge. And not only that, it can also, provide you the better working environment. We also done the from our investigation, we found that if any cooks use this technology for about 10 to 15 years, their lifespan also will increase by about 2 to 3 years. So they won't get any kind of respiratory, problems or health issues, and they will be very healthy. There are many lateral benefits. And this technology is highly recognized by almost all ministries here. And this news, may across nearly about 260, the medias reported about this technology, not only here in India, but also in the US and Germany and many more countries. And so this is also secured the first place among the 250 project, funded by the government of India. There are many recognition we got, and recently we also got the Abdul Kalam Technology Innovation National Fellow for this award. And very recently, I was also elected as a fellow of INAE for this work. Okay, in future, we are planning to, introduce the hydrogen. That is our goal, and already the work is already started with this porous radiant burner technology. So we will be using, LPG, maybe mixed with hydrogen, or the LPG with CNG. Different option we are exploring it. The biogas now, recently we made a big biogas, these burners, which is already supplied to many dairy industry, because in the dairy industry they produce tons of biogas per day. Most of the dairy industry, what they do, they could not consume the biogas, just simply they let it, because the biogas produced from the milk, that will have high moisture content. So with high moisture content, none of the conventional burner works. And even they have this trying to implement it, but they have both the biogas and LPG. When LPG biogas burner is not operating, then they will use LPG. But at the end, they will end up with using only LPG, because they need to have the continuous firing. So after this one, and we implemented our solution in one of the leading, the dairy here. I think you must be heard about the Milky Mist. There is a Milky Mist. There is a very famous ice cream company. And, they also make the frozen chapati and parota and all these things. Every day they produce nearly about 50,000 parotas. Okay, earlier they used they have been using only the LPG, which again they are paying for it. And they could not use the biogas. After this, we implemented our solutions, and they are using for the last 5 months, they are using it without any trouble. And so the ethanol also we are planning to do it. We are planning to go in a large scale application. Another one missed out here is the DME. DME, of course, soon that is going to be the another future fuel. That also we are planning to work. So we got several patents, 10 granted patents already. 10 patents are already granted, and a few more are in pipeline in this one. And so various recognition we got for this technology, including the recently this fellow of National Academy of Engineering, Abdul Kalam Technology Innovation Fellowship, and many other things. Of course, we got it for this the work. Yeah. So anyway, I wanted to have more discussion from the audience. That's why I made it little fast. And now this talk is open for discussion. And please, you can ask.
So thank you so much, sir, for the wonderful presentation on this burners on which you have worked. It is truly a well appreciated work. So I think it will make a revolutionary impact on the household applications, and really useful for the human being. So, sir, I wanted to ask you that the material which you have used for the making these burners. So, can you explain something about the materials?
Okay, so you can see this. Maybe I will have. Let me see whether I have the better picture or not. Yeah, maybe you can see here. So what you are seeing, there is a gray color one. Okay, that is a SiC silicon. Basically, it's a majorly silicon carbide. This is doped with rare earth metals. So there are a few rare earth metals. It's again mixture of mismetals and nickel, then little bit of the you can say the chromium and all these things. That is doped mainly to have the structural stability, because otherwise when you use the ceramic, when if you heat it and then when you cool it, it will break. That you may not have the structural stability. To have the better structural stability, and this will be the along with a little bit of sodium silicate also added. Okay, that is the one material. And then another material below, then below one we have another one matrix. That is the again alumina. Here there are three types of alumina: coarse alumina, fine alumina. And again, for joining this one, we will also little bit the sodium silicate will be used, and there will be sintered at high temperature up to about 1700 degrees Celsius. Sintered. After that, then it will undergo the normal curing process. Okay. So this caviar, this will be the alumina block will be produced by the normal pressing and then followed by firing. Whereas the silicon carbide, this combustion zone material, that will be produced through the foaming process. So we have the NDA and all this with a couple of companies, and we given the technology to them, and they are producing for us. And the technology is already transferred to 3 companies. Okay, they were but now they have started manufacturing, and this is also commercially available now.
Yeah, thank you so much, sir, for explaining in detail this much, because yes, really impressive work. I am very thankful to you for this presentation, because it is really very surprising that you are working on the real application of the household for the household purpose. That is usually means for
Yes,
everyone. It is very useful.
what I have shown is only the very one application. We
Yes,
have many applications. In fact, because of the time limit, I have not cited.
yes, sir.
This also largely used in the industrial application. Now we are using in the industrial application. You take any industry where the thermal management is required up to about 1000 degrees Celsius. You can use this technology even for the pharmaceutical material industry, boundary industry. For in boundary industry, for preheating the dyes. In fact, this burner is used extensively in the cold industry, cold making industry, where they need to keep their mold above 600 degrees Celsius. For preheating, they are using it, and many such application. Even for food drying and pharmaceutical industry and sweet industry, bakery industry, they are using it. Many industry they are using it.
Yeah.
Yeah.
It's really wonderful, sir.
Yeah.
So, any other questions from the participants?
Yeah, you are please. You are free to ask any questions. No, you don't be hesitate. Okay.
Sir, I'm having one question that is it possible to have this in technology in the direction of aerospace application in the direction of combustion over there?
Aerospace application. You
Yes,
mean
sir.
to say for the missile launching and all these things?
Yeah, missile launching as well as the control combustion I'm talking about, where we can have the burners where they are generally going to used over there. Sir, I am audible? Some issue is there.
Yeah.
Aman, please check it out.
So, there is some issue from
200 degrees Celsius. Yeah, then you may lose some efficiency. When you go with the metallic matrix, what happened? The efficiency, the emissivity will drop down, because these matrices are designed to have emissivity of about 0.98. The emissivity, whatever you are seeing gray color material, that is about 0.98. Okay. If you go with the metallic, it may be, you may get maximum about 0.8 or 0.85. So definitely then there will be you have to sacrifice the heat transfer.
No.
Yeah. Yeah.
Sir, one more question from my side. How did you optimize the design of these burners?
Yeah, so the design of this burner, basically, if you come to the Yeah, so where is that? Yeah, if you see here, so we have the several components here. The one is a brownish color is the combustion zone. Here we have the porosity plays a major role. Porosity and thickness of the burner and diameter of the burner. Even the below here we have the again the this preheating zone. Here we material we have the alumina. Again here the thickness, porosity and diameter. Many things are there. Again the length of the mixing tube and the diameter of the mixing tube, and then through the fuel injector, then we are injecting the fuel at certain velocity. There are many parameters. Okay, if you disturb one parameter, then the combustion will not be stable. Very, very crucial. So what we have done initially we have done the in a simulation on the combustion model. We simulated the combustion model, okay, with the help of the COMSOL multiphysics, and earlier also we used the Chemkin. And then based on this one, we have optimized this all the parameter like the porosity of the combustion zone, thickness of the matrix, and the thickness of the preheating zone, and the porosity. All these things we have matrix. And then again the air fuel ratio, and that air fuel ratio, and again the air entrainment ratio. That is the ratio of the the nozzle diameter to the slot diameter. Here there are slots. If you look at this, there are slots here. This slots area and versus the nozzle area, many parameters. So this is almost like a 3 years of work. And through the rigorous thermal modeling, all these diameters are optimized. That's the reason we are getting the stable operation, because when you go to the temple scenario, in the temple, the kitchen is expected to operate almost 10 hours continuously. Okay, if anything has happened in between, there is a margin. Almost in the Srikalahasti temple, they are feeding nearly about 7,000 people, minimum 5,000 to 7,000 people having meal during the lunchtime. Okay. So if then any small disturbance happen, our whole process will be hampered. So they cannot take any risk. So far we have never experienced any delay in supplying the food. Okay, this all about the the system thing. And I will tell you here, our burner operates with lean mixture. Here the equivalence ratio is varies from 0.65 to 0.7. Okay, whereas the conventional burner, the equivalence ratio, basically the conventional burner operates with rich fuel mixture. That means the equivalence ratio will be always above 1. Here in our case, the equivalence ratio is less than maybe around say 0.65 to 0.7. That is less than 1. So always it operates with the lean fuel mixture. That means more air and less fuel. That's why we could get 100% combustion. Nearly the combustion efficiency nearly 100%. Okay. There are many unique features with this technology.
Yeah, literally, sir, it is a long journey
Yeah.
from
We
starting
started this work in 2008. Okay, 2008, and it went through the different one. We started with the different material, and 2014 we could develop the prototype, and we have done the field trial. But again, the materials failed. The material could survive only for a few hours. After that, it became into the powder, and then there was a flashbacks, and then investigated. Then we went for the optimizing the material composition. Then finally we reached. And 2000, again around 2020, we reached the final composition. Then there are issues with the mixing chamber. Again, the mixing chamber started cracking, and there are several. And then the tube. Then sometime after, when you use it continuously for about 10 to 15 hours, even the silicon carbon material itself started melting. There are several issues we faced. Okay, so we carefully addressed. And so finally in 2022, and finally we could reach the final version. Now it is commercially, it is in operation in several places.
Yeah.
Sir, myself,
Okay.
A.K. Rai.
Yeah, please.
Sir, I wanted to know about the pipe. The mixing of the fuel air particles where it is happening is the same of materials and design. Everything is same with the PRB and the conventional burners?
No, it's a different.
Different.
And the length and the diameter, everything is carefully selected here. Even if you see the slot, whatever the
Yes.
slot you are seeing, the slot is entirely different. Okay, everything is different. You cannot use the conventional burner mixing tube here. Even if the height little bit if it varies, then you will have the flashback issue. Okay, the height
Okay, thank
also. height also matters, because when here in this case, the jet well, again the pressure also, the conventional burner, if you see the conventional commercial burner, they will inject the LPG to the pipeline. Even the pressure around 2 bar, 2.5 bar directly go into the burner. Here we have a special regulator. If you see the burner, most of our burner comes with a special regulator. Maybe if you see here, can you see here in this? There is a special regulator. This special
Yes.
regulator, this will be there in all the burners. So irrespective of the downstream pressure in the upstream, it will send only 0.5 bar. We can vary. Maybe it can operate between 0.8 bar to 1 bar. That is the optimum pressure we can set. Okay, and then in each burner we have the kind of a flame arrestor. In any bad situation or any kind of extreme situation, it never allow the flame to travel back. So we have the flame arrestor, and this even suppose the line pressure is too high, when it comes here by mistake then it may lead to any accident. So to avoid that, we have a special regulator. Okay, so everything is fine tuned.
Thank you, sir.
Yeah.
Yeah, thank you so much, sir.
Yeah.
If any participant is having any question, you may ask, or you can write in the chat box also. If you
Yeah, this is normal day-to-day application. I thought
yes,
the people participant will be interesting. That's why I have taken this topic.
yes,
I
yes,
initially thought of giving a talk on hydrogen energy, hydrogen storage, and other related application. Anyway, I think some of the people are already there, so probably they may talk.
No issue, sir. If there may be any possibility, then we will inform you 1 day or 2 day earlier if
No,
it
it's
is
fine. I
possible.
think you can give opportunity to the other speakers. Yeah, they
Yes,
will be
yes.
more excited
But
because I am.
it
No,
yeah,
I
we are
supervised, yes, in this area itself, around 10 students are already graduated.
yes, yes,
So already I have nearly 42 PhD students guidance so far. So many.
yes.
Yeah.
So nice of
Okay,
you,
then
sir.
thank.
And
Yeah.
yeah, it is
So if
truly
there is no, there is no
yes,
questions from the participants, and we can, of course,
yes.
wind up the
Sure,
lecture.
sure, sir. You can stop sharing and thank you again for means accepting our invitation and
Yeah.
giving your valuable time in this FDP.
Yeah.
And we would be happy to have you on other sessions also. We will reach to you
Yeah.
in next
Yeah,
2
and
months.
one more request to all the participants. And of course, I'm actively not. This is porous study in burner is one of my area, and in addition to that, I'm also working on the hydrogen storage. This is all at the industrial scale. We have many projects, and Tirupati also soon it's going to get the Center of Excellence on Hydrogen Energy. We are going to establish a national center on hydrogen energy. Okay, where we are going to concentrate many application: hydrogen storage, hydrogen purification, hydrogen production, hydrogen compression, and hydrogen utilization, including the IC engine, hydrogen-based IC engine, then hydrogen-based heating and cooling system, and hydrogen-based burner, and fuel cell, and then many application in a large scale we are concentrating. And apart from that, I'm also extensively working on the refrigeration and air conditioning thing, and I have many PhD openings. So if you are interested, if any of the students or you are, maybe you can pass this information to the institute. If anyone is interested, and if they can of course approach me, I can take. So most of my scholars are in the highly reputed, they're holding highly reputed positions, and more than 10-15 students are there across the globe, and and many students are in NITs and IITs, other national labs. They are leading a big position. Okay, so we have, of course, big among India. Our group is one of the leading group, particularly in hydrogen energy, and even in globe also. I'm also one of the editor in International Journal of Hydrogen Energy. So yeah, if anybody is looking for kind of research higher studies, particularly either MS or PhD, and the student should be very serious and dedicated kind of a student. So if you have any such things, please let me know. I will happy to provide the opportunity. Okay, thank you.
Thank you so much, sir. Thank you so much.
Thank you so much.
Yeah.
Now we are winding up this session. Thank you so much, all the participants, for joining this first day of the FDP. And tomorrow we will meet at 9:30 a.m. sharp. Thank you so much.
Aman, tomorrow we are not having that session. Around 10 we are going to start.
Okay,
Right?
okay, okay, okay.
10 or
Sorry.
10:30. Please check it
10:30.
out.
Yes, 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 yes. Tomorrow we'll be meeting at 10:30.
Tomorrow, the Tiken sir session is there, right?
Yes, yes, yes. Tomorrow we'll be having at 10:30. So Dr. Gaurav Dwivedi will deliver the session, and on Tuesday, Tiken sir will be there.
Okay.
Okay, thank you so much, all the participants, and I request EICT Academy to wind up this session and for all the participants.